Okay, number 3. Let G be the group of integers with addition. Find a subgroup of sim G, the permutations of all the integers, which is isomorphic to the integers. Okay, so this is just like number 2. This is just like Cayley's theorem, which is about, talk about how you can find a subgroup of the symmetric group. Yeah, subgroup of sim G for any G, which is isomorphic to G. Well, all number 3 is asking is do that specifically for Z. So really, number 3 is just an application of Cayley's theorem from number 2, where you're filling in a specific group Z. So you just got to talk about how that works and what that is. So let's use the same formula from 3, which was where you make the following isomorphism. You say phi that takes an element of G, or I'll use it takes an element G of G and turns it into lambda G. And what is lambda G? Well, lambda G is the function that takes in an element x and turns it into G times x, right? So, and I say G times x as in the operation of the group, but in this case, our group is addition, isn't it? So I might as well call it G plus x, right? So, and you could also, rather than use that arrow notation, you could just as well write it this way. Say that function, you plug in G and you get, you plug in x and you get G plus x. And similarly, here you plug in G and you get this function, lambda G, into which you plug in other elements of G. Okay, so anyway, so for example, so phi could take in a number, the number 3, and it would turn it into the function lambda 3. And that function lambda 3 is a function that takes in stuff like 5 and turns it into 3 plus 5. And it takes in everything, actually. Uh-oh, 1 second. That's been happening. There you go. It takes in anything, actually, and it just does that to it. It just adds 3. So the idea is that all of this set of lambda g's, or maybe we could say lambda n's if you prefer n for integers, all of these lambda n's together with composition is just like z in the first place, is isomorphic to z in the first place. So we got to talk about how. Can I just clear like a whole section? Any way for me to do that on here? No. I'm not used to writing on the browser like this. So the idea is you got your integers over here. Uh-oh. You got your integers over here. Of course, it goes on forever in both directions. And then you have your function. Man, this is really struggling now, sorry. You have your function, phi, that maps between here. This is z over here, and it's mapping to a subgroup of sim G, so which contains lambda negative 4, lambda negative 3, lambda negative 2, lambda negative 1, lambda 0. Now lambda 0 is the function that adds 0, so that's the identity function. So all of these things on the right are functions that map integers to integers, so they're permutations of the integers, or permutations of G. And in fact, these two groups on either side, so we'll call this H, where H is a subgroup of sim G, or sim z, I could say in this particular case. Yeah, so that's of course not all of SimG. There's lots of permutations of the integers, lots of bijections from the integers to the integers. You can flip them around, make everybody negative. You can zip them together in a weird way. There's all kinds of weird ways you can do it. So this is quite a small subgroup, but it is a subgroup, and phi is in fact an isomorphism. Now you don't really have to prove that. Because it's basically what you already proved in number 2. Well, I don't have the solution up here, but in number 2, you already proved that like this setup, the phi going from the elements of G over to the lambda sub G's over in sim G, that setup, phi is always an isomorphism. So you don't really need to work it out, but you could say phi n lambda n composed with lambda n on x. Well, if you think about what that is, that's just n plus m plus x ultimately, right? And so that's the same as lambda n plus n of x. So you can see that multiplication in the lambdas over here, so that's phi of n and phi of n. That's equal to addition in the exponent, or in the subscript, I should say. So that's phi of n plus n. So the point is, yes, indeed, phi is a homomorphism, and it's not hard to show that it's also an isomorphism. And again, we don't need to get into it. It was part of number 3. So yeah, so the answer to the question, what is the subgroup that is isomorphic to G? Well, it's this thing that I called H, which is the set of all lambda n's, which do this, right? They turn x into n plus x, or you could say x plus n, it doesn't matter. They're all of those for every n in Z. So you don't have to write that part on the, you don't have to write this part, but you can, just to clarify what lambda n does. And actually, to be perfectly correct, I did that wrong. For that notation, I need to use an arrow with a little thing there. So yeah, so there you go. That's the answer to the question, is that subgroup. So really what I was looking for this one was just kind of discuss the situation for integers specifically, right? Some people got perfect number 2s and left number 3 blank, which is really unfortunate because number 3 was really just number 2 but applied to a specific thing, to a specific G. So yeah. Yeah, anyway, so that's number 3. Okay, moving on. Whoops. This thing's broken again. Hopefully it'll fix itself in a second.